Okay, so the most beautiful thing in physics in general is analogies between when the same physics shows up in very, very different contexts. So I am looking forward to seeing one of the most beautiful demonstrations of this unity of physics. And Brett Marston is by heart quantum condensed matter physicist, and being quantum condensed matter physicist, he decided, for the reason that I don't understand, to study waves in the ocean, which seem to be, yes, condensed, but not quite quantum usually. And he did there something that is, in my opinion, very beautiful, which is not surprising, given that he is a vice president of APS.
I'm not sure that's, I think that is kind of a strange combination.
People might start questioning your ability to reason.
All right, please, Brett.
Thank you. Sure. It's a pleasure to speak to you today. And also, I've been really enjoying meeting a number of you and seeing this space that's new to me since last time I visited the campus. We were over in the other building, so really congratulations on this beautiful area. So I want to tell you about this work that my collaborators and I have been doing, and waves of topological origin in the fluid Earth system and beyond, possibly beyond. It really began with my French collaborators, Antoine Benaille and Pierre Delplace, and it's expanded to a larger group, including Chris Lee, who's sitting back there. And actually, there's more people involved at this point too. I think we're just beginning to sort of understand some of the possible connections between lessons that we learned first in the quantum realm, and now we're applying to the fluid Earth system and other fluids. So I want to begin with this quote from Richard Feynman. The next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see that the water flow equations contain such things as the Barber-Pole structure of turbulence one sees between rotating cylinders, rotating Collet flow. Today we cannot see whether Schrödinger's equation contains frogs, musical composers, or morality. Whether it does not, I'm not going to attempt to answer that question. But I do want to tell you about a little bit of progress that I think we made in understanding some qualitative content of equations that you have to work much harder if you want to take a direct approach to understanding them. And that's based on topology, and the idea is that topology can turn some complicated problems into simpler ones. So just to recall what topology is, it's basically the qualitative shapes of things. Things don't have to be in space, but they can be in more abstract spaces. But you know, the famous example of a coffee mug that has a hole in it, it's a genus one surface, can be continuously deformed to a donut. The Mobius strip, where you have a non-orientable surface, you go around, what seems to be inside becomes outside, versus an orientable surface, a qualitative difference between these two shapes. And something's a little bit closer to what I'll tell you about today, the hedgehog theorem, which says that if you have a perfectly spherical hedgehog, or a spherical hedgehog, it doesn't have to be perfectly spherical, you wouldn't be able to comb all of the quills on that hedgehog without leaving some sort of defect, a lick or a bald spot. And when I was on sabbatical in France, we had these hedgehogs in our backyard, and I was raking the leaves, and I unearthed one of these that was actually going into hibernation, and didn't know what to do about it. got some help, but this was like a little signal maybe indicating to pay attention to topology, and that's at the time when we started thinking about our this collaboration with Antoine Yanai, although nothing had really crystallized at this point. So the outline of the talk is I want to review a little bit about these waves that are very important in the Earth system, and they're important to this climate oscillation, the El Nino. And I'll tell you a little bit about some observations and some simple simulations of these waves, and relate this to the presence of broken discrete symmetries in the system. And then switch briefly to the quantum Hall effect, which is going to provide the analogy that connection to some of this topological physics. And that's going to lead me to sort of the heart of the talk, the shallow water equations, where we'll be able to see with some very simple mathematics that there's some non-trivial topology here that leads to the prediction of these waves. And that's through the presence of the winding number. And we're going to look at actual observations of the stratosphere of the Earth where we can measure this winding number and directly show that there's non-trivial topology of a certain class of waves. And I'll tell you about some experiments that we've been doing with magnetized plasmas looking for similar waves. So this is a view of the Earth's ocean, Pacific Ocean, and it's based on satellite measurements of the height of the ocean using microwaves, radar basically. And so this is red represents higher than average, blue is lower than average. The amplitude of this wave is, or this oscillation is about plus or minus 20 centimeters. So this data has been filtered to remove tidal motion, to focus on lower frequency motion. And if I set it into motion over a 3-month period, you can see the propagation of this wave moving along the equator. That's the equatorial Kelvin wave. That's going to play a crucial role in what I tell you about. And when this wave moves over here, well, I should mention that the color also represents an anomalous temperature of the ocean. When you have warmer water, it expands, and therefore the height of the water is higher over here. And when there's a pool of warm water off the coast of South America, as there is at the present moment right now, then we're in the El Nino phase of the climate oscillations, the largest oscillation of the Earth climate system on the timescale of years. And it has large scale effects. So probably some of the atmospheric rivers that have been hitting California right now can be attributed at least partially to this El Nino oscillation.
Is the temperature differential you were mentioning, you said that, is it associated with the surface, or and how big is the amplitude of the radiation?
So there's a surface manifestation in warmth. The wave is actually at depth, or down at the thermocline, the below the first 100 meters or so of the ocean water, but it manifests as a warming on the surface, and it's a few degrees.
People often speak of it, El Nino, as an upwelling along the coast, and this doesn't look like that at all.
Well, actually, so during the El Nino, it tends to, because you have this warm water on the surface, it inhibits the upwelling of cold, nutrient-rich water. And Peruvian fishermen noticed that their catch was reduced during this phase. That's why they called it named it this El Nino. It happened around Christmas time. And so that was like 100 years ago that it was observed. So this just indicates some of the worldwide manifestations of this El Nino. So warmer sea surface temperatures over here, but it also affects the track of the storms and so on. Is as I say, a very large, important climate oscillation. And back when I was a graduate student, I inadvertently got interested in this because I noticed that there were, I was looking at the average temperature of the Earth, which I noticed fluctuated from year to year, not due to global warming, but just due to the natural fluctuations of the climate system. And so that's represented by this dark line. And then I noticed that it correlated strongly with the amount of carbon dioxide being added to the atmosphere or subtracted from the atmosphere above and beyond the long-term growth of carbon dioxide due to human emissions. So in other words, there's a correlation between fluctuations in temperature, especially in the equator, and carbon dioxide in the atmosphere fluctuations. And this is held up all the way to the present. At this time, we only went from about 1958 to 1990. And it represents a kind of positive feedback because when the Earth is warmer, there can be more carbon added to the atmosphere through a variety of processes like more forest fires during an El Nino. And most of these temperature fluctuations that we're seeing here are associated with El Ninos. So El Ninos are not just affecting the global temperature of the Earth, but they're also affecting the carbon cycle. So it's a very complicated and interesting system to think about. And we know a lot more about it than we did back here in 1991. So now I want to start to get at the physics of this wave. And so what I'm going to do is look at a wave model where I have a stratified fluid. I have a denser fluid below a lighter fluid. So that's what we call stably stratified. I'd like to stay that way. And if we perturb it, if we make, say, a bulge of this denser fluid, it would like to push out and we'll get an oscillation. And so on a sphere, if we drop a rock into a pond, waves emanate out, but they go to the antipode of the sphere and pass through each other, and then they just come back and forth because the sphere doesn't have any boundaries. So this is what we call a gravity wave, as opposed to gravitational waves, which are the general relativity waves. And it's due to the restoring force in the vertical, due to this density difference, so force of gravity. And this is a view on a cylindrical projection, just showing that antipode and the wave passing through itself. This is a low amplitude wave, so nonlinearities aren't playing a role here. But now I want to turn on the rotation of this sphere. So I want to turn on the Coriolis force. The Coriolis force acts in the horizontal as a separate second restoring force. So everything will be the same in this simulation except for the rotation. So the initial condition will be the same. And now we're going to see a very different behavior. Now the wave is confined to the equator, and you can see it's a non-dispersive wave that propagates along the equator to the east. This is the Kelvin wave, the equatorial Kelvin wave. And it was first understood by geophysicists in the 1960s. There's a second wave called the Yanai wave, which is anti-symmetric with respect to the equator. So you can see that it's positive above and negative below, or vice versa. And you can also see that it disperses. So it's phasing. Its phase velocity is different than its group velocity there.
So it's rotating this way, right?
It's rotating
in the same direction as it provides.
Same direction as the Earth is, yeah. So if you want to play around with this, I have this app on the Mac App Store, free, GCM. And I use it for my research, but it has various basic models. So if you have a Mac, you can run it there. So let's talk about the symmetries that are broken in this system by rotation. So when we have a spinning planet, if we view that planet in a mirror, if we do a parity operation, it appears like the rotation has reversed. But then if we reverse the arrow of time, the direction of time, we run the movie backwards, that does a second reversal of the rotation. So the product of parity and time reversal leaves the system unchanged. The famous CPT theorem, where this is charge conjugation, I'm looking at neutral fluids here, so charge doesn't play a role. But PT is a symmetry of this system. And we can see that algebraically if we think about the how acceleration works in a rotating non-inertial frame. The acceleration in a rotating frame is equal to the acceleration in an inertial frame, F equals m, but then it has these two fictitious forces. The first one is the Coriolis force, and the second is the centrifugal force. And the Coriolis force, notice it has one velocity here, which has only one time derivative of a coordinate, whereas the acceleration has two time derivatives. So under time reversal, the velocity changes sign, but the acceleration remains invariant, and therefore we have to reverse the sign of omega in order to keep the equation invariant, which is just the algebraic statement here. Now, in the fluid Earth system, most of the motion is in the horizontal direction, and that means it's the vertical component of the rotation that plays the important role in the Coriolis force. So we take the local vertical normal of the rotation vector, which is pointing towards the north, and we find that that quantity F, which is equal to 2 times the angular rotation rate of the Earth times the cosine of the co-latitude. So that's the thing that's going to be 0 up here and pi down here. That changes sign across the equator, which is the famous thing about supposedly, well, in reality, high pressure zones in the atmosphere circulate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And the equator is the boundary between two phases of fluid motion that break time reversal symmetry in an opposite sense. That's the crucial observation, because that boundary, when we have two topological insulators, for those of you who already are looking ahead a little bit, that have a boundary between them, that's where we expect to find waves along that boundary of topological origin. So it's the breaking of time reversal symmetry in an opposite sense across this boundary that is what we're paying attention to. So in the case of the quantum Hall effect, it was David Thales who recognized most clearly, although there was some earlier work by Bob Laughlin and Bert Halperin, that topology plays allows us to understand why the Hall resistance is quantized very precisely in these plateaus. In fact, it's so precise that it's now the international standard for resistance. And so there's a picture of Thales. Mechanistically, the magnetic field acts a lot like the Coriolis force. It acts at right angles to the motion as a cross product to the Lorentz force. And if we think about electrons in the magnetic field in this layered semiconductor, then they're executing cyclotron orbits semi-classically. But on the boundary, they hit the boundary and they bounce. And so there is this motion in one direction, this unidirectional edge current here going the opposite direction on the other side, which makes it immune to backscattering from impurities, because the current has to go in one way, it can't go back the other way. So mechanistically, this is why the presence of dirt impurities in the material doesn't have a strong effect on the plateaus. Thales provided a deeper explanation in terms of topology, which I'm not going to recapitulate for you here because I'm going to tell you about it in the classical context of wave mechanics. And the magnetic field, of course, breaks time reversal symmetry in this very similar way to the rotation, the Coriolis force. So now let's look at how this works mathematically. And I wanted to introduce the shallow water equations, which is sort of the minimal model that supports this idea theoretically. And so again, we have a denser fluid underneath a lighter fluid. And I want to characterize the motion in two horizontal directions, x or y. and this fluid has some height. And I want to write down the equations of motion for that fluid. So these can be expressed in terms of conservation laws. The first law says that the time derivative of the height plus the divergence of the height times the horizontal velocity is equal to 0. This is nothing but the conservation of mass. It simply says that if this bulge is being pushed down, for instance, so h is decreasing, so dh dt is negative, that means that this quantity here has to be positive, which means that there's a divergence of this fluid. It's being pushed out, and the fluid is being conserved. Mass is being conserved. The second equation here is simply F equals ma. It says the time derivative of u, the acceleration, is equal to the two restoring forces. The restoring force of gravity, buoyancy, which involves the gradient of the height here, and the Coriolis force, the Coriolis parameter F, which I forgot to mention. That F parameter, it's called F because it's the same parameter that appears in the Foucault pendulum that tells you about the precession of the Foucault pendulum due to the rotation of the Earth, and how you can determine your latitude from the rate that the pendulum rotates. So here are the two restoring forces. And the only sort of mysterious term maybe is this one. This has to do with the fact that what we're really looking at is the acceleration of a parcel of fluid. So we have to look at what's called the advective derivative. The fluid, if we imagine labeling some fluid with some dye, we're looking at the acceleration of that fluid as it moves along. But I'm going to drop this term in any case, and I'm going to replace this little h by the average height here in a linearized approximation. So I'm going to look at linear waves because those are easier than nonlinear waves. And if the wave amplitude is not too large, this is a good approximation. So if I do that, then the normal modes of this system are described by a linear wave equation that looks a lot like a Schrodinger equation. And in fact, we have a linear operator, h, which if I'm working with plane waves in the x and y direction, so I assume translational symmetry in the x and y directions, then these derivatives can be replaced with wave numbers, kx and ky. And here you see F appearing with an I, that's signaling that there's time reversal symmetry breaking, for those who are familiar with this. And I can just diagonalize this linear operator to find the frequencies of these waves. And if I do that, I have this very nice spectrum that will be familiar to anyone who's looked at graphene, for instance. It has a zero mode here with completely zero frequency waves. And then there's a gap, and that gap depends on the rotation rate of the planet and goes to 0 as you turn off that rotation rate. So then you get just a Weyl fermion type dispersion, or it's not fermion, it's a Weyl dispersion, a cone coming out of this flat zero mode. And what is this zero mode? It's nothing but the fact that, again, these high pressure zones have circulation going around them clockwise and low pressure counterclockwise. There's no frequency associated with that motion. It's just steady motion. So we call that geostrophic balance. There's a balance between the Coriolis force and the pressure gradient. If we look at the wave amplitude here, so these are the two components of the velocity in the x and y directions, and this is the vertical component, we can see that there's the presence of a singularity. The phase of this wave in wave vector space changes by 2 pi as we go around the origin. This is the key topological thing that I want to focus in on. And I want to give you a sort of more graphical view of this. So let's imagine we vary the Coriolis parameter here. Here in the South Pole, it's at its maximum negative value. North Pole, most positive value, 0 at the equator. And here are the dispersion of our waves, say at the South Pole. And if I look at the phase of this complex number, then I see that it's represented by an anti-vortex going around the origin in wave vector space. It has a winding number of -1 because these little arrows, which represent the phase in complex of this complex variable argument, as we move around in wave vector space, it changes by -2 pi as I go around and increase by 2 pi. This can be done in a gauge invariant way, this sort of technical remark, by multiplying the component, say the y component of velocity by the complex conjugate of the height. At the North Pole, if we do the same thing, we have a vortex, all right? And I've colored the bands here to indicate the topological charge of these, each band. The green geostrophic mode has no winding number, but up here we had blue negative for the anti-vortex, and in the positive frequencies over here, though, on the other hand, have a vortex. So if we follow the sign of, if we follow, say, the anti-vortex, it starts off as a positive frequency mode, but then becomes a negative frequency mode as we move across the equator. And that tells us that there should be some modes near the equator that have near zero frequency. This is something called spectral flow, for those who know. So in fact, say here at zero rotation, then these two bands, the upper and lower bands touch. They no longer have definite topological charge because a topological transition is occurring. And here's the dispersion. We now have up here the bands at high positive frequency, bands at high negative frequency, and now these new bands, the Kelvin and Yanai wave, that connect the negative or zero frequency modes to the positive frequency modes. And when I include the fact that the Coriolis parameter is actually varying continuously with latitude, then these waves that didn't have any dispersion become dispersive. They're known as Rossby waves. They're the most important waves in the troposphere. They're basically the thing that governs the passage of weather systems up here at mid-latitudes. So that's the picture in a summary. There's a change of the winding number by a factor of 2 as we move across the equator. Because the winding number changes from 2, -1 to +1, there should be 2 boundary modes, and those 2 boundary nodes are the Yanai and the Kelvin waves. So we can also express this in terms of Chern numbers, the argument is the same way. In fact, that's how we originally thought about it. Now we're thinking more in terms of winding numbers because it turns out to be a more flexible tool than the Chern number for some technical reasons that I'm happy to go into. Okay, so if we look at what had previously been discovered by geophysicists, Matsuno originally, by directly solving the shallow water equations with a continuously varying Coriolis parameter, which takes a little bit of work because no longer can you work with plane waves. You have this non-trivial dependence of f in the latitudinal direction, leads to Hermite polynomials, something any physicist can solve. Now, it's not that hard, but it requires some work. You're solving partial differential equations instead of just diagonalizing a 3x3 matrix. They found the dispersion of these waves. Here's the Kelvin wave and the Yanai wave. Wave number going down here, frequency going up here. And when we got referee reports on our paper, we had this remark from one of the referees. The question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I have asked the question myself and have been unsatisfied with my own answer as well as that of other atmosphere and ocean scientists. So what this referee was saying is that I think the geophysicists realized there was something funny about these waves, but they couldn't quite put their finger on what was funny about it. And that's because they hadn't been sitting in condensed matter seminars where we've been talking about topology and topological waves for the past 2 or 3 decades, and didn't see that there was this phase singularity in the wave function, or at least didn't know what to do with it if they noticed it at all. So I want to now turn to some observational evidence for these waves. Well, we saw that satellite reconstruction, but let's look at the dispersion of the waves. So one way this can be done is that as this pool of warm water moves across the Pacific, there are some clouds that follow it, because warm water will tend to make clouds form, more evaporation. And so by looking at cloud brightness with satellites as a function of space and time, one can work out the power spectrum of effectively of this warm pool of water. And if we do that, or if climate scientists do that, they're doing basically the analog of an ARPAS experiment, an angle resolved photoemission experiment, to just figure out what the dispersion of the waves are. So this is a ARPAS experiment for a topological insulator showing 2 waves of topological origin on the surface of a topological material, topological insulator. Here's our theoretical dispersion. And here are the results of looking at that power spectrum of the clouds. This is looking at the part that's symmetric with respect to the equator, and the part that's anti-symmetric with the equator, that is consistent with the dispersion that we see up here, this linearly dispersive Kelvin wave and this dispersive Yanai wave. So that is some nice confirming evidence, kind of the analog of this ARPAS experiment. But we asked ourselves, can we directly discern the non-trivial topology of these waves? After all, we're living inside this topological insulator. So it's a lot easier to probe the atmosphere than to get inside some small condensed matter system and try to determine whether the wave function has a singularity in it. And so what we did is we looked at data that's been collected from the stratosphere. The stratosphere is a stratified fluid. So it's the place where there are very clear waves, gravity waves. And we looked at a region of the Earth that is away from the equator to try to see whether this phase singularity appears. So this is just a theoretical plot first, again, of this singularity, looking at this gauge invariant winding number. It's basically this definition. So the normal modes are unique only up to an overall phase, just like a quantum mechanical wave function. I want to get rid of that phase ambiguity. So that's why I multiply one component by the complex component of the complex conjugate of the other component. That leaves us something that's independent of the overall phase of our wave function. And here, depending on the sign of the Coriolis parameter, we see again this transition from an anti-vortex to a vortex. This is for the high frequency waves. For the low frequency waves, the ones that were just completely zero frequency, but then become slightly dispersive when we turn on the effects of the variation of the Coriolis parameter with latitude, then we have actually a domain wall where the amplitude vanishes along at this point kx equals 0. So it's not allowed to form a closed loop. Our topology says that we need to look at continuous deformations. This would be a discontinuous deformation because the amplitude goes to 0 all along this line. So there's a clear distinction between these low frequency Rossby waves and the high frequency Poincaré waves, Poincaré gravity waves. And here, looking at the stratosphere, there's a very interesting phenomenon that's been known for quite a while called the quasi-biennial oscillation. We've already met the El Niño Southern Oscillation. This is an oscillation that occurs in the winds up in the stratosphere near the equator. And you can see that it's really periodic phenomena, which is kind of amazing for the climate system. Most things are not so regular. It occurs about every 2 years, but it isn't exactly every 2 years. It's like every 22 months. So that's why it's called quasi-biennial. It's kind of strange that it's not synced with the calendar year or some harmonic of it. And so there's this reversal in the direction of the east-west winds at altitude. And the Kelvin waves are implicated in this reversal along with other waves. So there's something interesting that's been known for a while with the stratosphere in this oscillation. I just want to show you this just as another example of a climate oscillation. So anyway, we looked at data that's been collected from balloons and satellites, and then it's been processed in this this process called reanalysis, which is basically using a climate model or a weather model to interpolate between the irregularly spaced observational data to try to give us a regular spacing. And we're looking at this region between 25 north and 65 north, where the Coriolis parameter just has one sign. And here are those theoretical plots. And then if we calculate with the data this gauge invariant quantity, then we see that at frequencies of 1.5 cycles per day or 1.8 cycles per day, there is this vortex in the in this phase. But if we go to low frequencies, there's this domain wall, consistent with our simple shallow water model. Now, we don't need to use that simple shallow water model. This also holds for continuously stratified fluids, as we've done some further work showing that that's the case, and it also is immune to some shear that can be imposed on the flow. So we know that this kind of topological argument works in these more complicated situations. So it's probably, it's not completely surprising that the atmosphere actually evidences this from data. So non-trivial topology is found. We looked for a seasonal dependence. This is the meteorologist's definition of the seasons. So winter is December, January, February. Spring is March, April, May, and so on. You can see that there's not very much any difference here. Again, we have a winding number of 1. Here I'm looking at a correlation of u, the x component of the velocity, instead of v. So the angle of these arrows has rotated by 90 degrees, but the winding number is still 1. If we go down lower in the atmosphere, just like 5,000 feet up, the atmosphere in the troposphere is much more turbulent. There's a lot of turbulence from storm systems, but also just heating of the surface and airflow over mountains. And there, if we repeat this experiment, this analysis, then we find that there's no clear signature for these gravity waves. And that's as expected because the troposphere is not very strongly stratified. And so the restoring force, the buoyancy force, is much weaker, and the signal from the gravity waves is itself much weaker. It's there are other waves that are dominating the spectrum. Now, a number of years ago, we had a search to hire a new condensed matter physicist, and when they came into my office, I handed them this book, Geophysical Fluid Dynamics, which I had bookmarked up here, and I asked them to open it up, and this is what they found, this dispersion relation, and they immediately understood what was going on here because they had seen this kind of plot over and over again in seminars like this one. So this is an example of what the Kelvin originally looked at, which is a wave that moves along the coast. So he was interested in waves in the English Channel. So instead of having the equator where the time reversal symmetry is reversed, here we have a situation a little bit closer to the quantum Hall effect where the material just ends at some point. The fluid just ends and you have a coastal boundary. It took a while this actually is a more subtle, requires some more subtle topological analysis if we're using the Chern number. But my French colleagues figured out how to do this, wave topology brought to the coast in physical review research. And here's a wave tank experiment demonstrating this. This is looking down on water with oil covering it. And so this tank here is not rotating. There's a wave generator here, and you can see the oscillations. Over here is the same tank, but in rotation. And now you can see the wave is propagating along the coast in this chiral sense due to the rotation. So the camera is rotating with this wave tank, just to be clear. So we're in the rotating frame. And here's Kelvin's paper from 1879 on gravitational oscillations of rotating water by Sir William Thomson. And it's very readable. If we open it up, we find this wave function, which has exponential localization with a linear dispersion. So this is surely the first time anyone has solved or written down a wave of topological origin. Although he didn't have a topological explanation, he directly solved the wave equations, the shallow water wave equations, and found this form. So a little bit of the history, if you want interested in the history of that, of Kelvin's work and our work and others, the Quantum magazine had a nice article about this last summer. Although the title was a little bit misleading, a little bit exaggerated. So there are lots of other oscillations in the climate system, and that are more poorly understood than the quasi-biennial oscillation. And here's one of them, the Madden-Julian oscillation, which people have been searching, asking the question, is there a simple model that captures the basic physics of this oscillation? There's lots of competing models right now. It's a little bit like high temperature superconductivity, I'd say. There's all these different models. It's not really clear which is the right one. And what this is a pattern of rain that moves across the equatorial Pacific. It typically starts in the Indonesia area, moves across, so it looks like it's confined towards the equator. And a question that we have is whether this has some sort of topological physics in it or not. I don't know the answer to that, but we're trying to develop some tools so that we can probe this phenomena and see if there is some sort of topological physics going on that might explain the robustness of this phenomena. My title mentioned the and beyond. Various groups have been thinking about astrophysical applications of these ideas. So this is looking at the interior of a star like the sun. So a solar type star has two main regions. It has a radiative zone and a convective zone. The radiative zone is in the interior, deep interior, and the convective zone is outside. And these represent those terms tell us that there's a change in the main mechanism by which heat is transported to the surface. And it has to do with the stratification. And in this paper, they argue that there are topological modes that could be observed in stellar observations. In this paper, it focuses on something called the tachocline, which is this transition region between the radiative zone and the convective zone that's thought to be important for the solar dynamo, the magnetic field generation. And so the magnetic fields may be implicated in some waves of topological origin in this system. We've been doing a plasma experiment to look for these waves. You might ask, well, so what's a theorist doing working at a plasma facility? I asked myself that question, especially when it's a very difficult experiment, at least for me. This is the large plasma device that's at UCLA. It's basically a solenoid that's like 100 feet long that has a plasma in it. And so it can be magnetized. And the magnetic field, as I mentioned, has an effect similar to the Coriolis effect. And what we're trying to do is produce waves of topological origin that we predicted based on the plasma equations here. So we're shining microwaves on this plasma to see if we can find these waves being generated, and whether we can find some evidence that they have a topological origin. And so the reason we're doing this is because plasma physicists haven't been going to condensed matter seminars, and they too haven't been thinking about waves of topological origin until recently. So we decided we had to do this experiment. So this is our theoretical prediction of the dispersion. Again, there's a gap because there's two frequencies. There's a plasma frequency and a cyclotron frequency. And if you set things up right, then there's a gap, and a dispersive mode should travel along the boundary of the plasma, between the plasma and the vacuum. And so these are some simulations that one of my senior thesis students did, looking at these propagating modes going around the cylinder of this, so the magnetic field's coming out of the cylinder here. This is looking at it with some perturbation in the plasma density, showing that that perturbation doesn't cause any backscattering. The waves are traveling around. We go in a different frequency that's not in the gap, then those waves lack the unidirectional topological nature that we saw previously. Here's just a view of this machine. Each flash is the plasma, so it lasts for milliseconds. And these are various probes that we can insert into the plasma to measure the electric or magnetic fields or density. And so we launch the electromagnetic waves with one probe and then scan for their presence with another probe. And this is just showing kind of the scale of this device. This is just looking down at the plasma. And this is one of our antennas that we use for these gigahertz microwaves. We had problems with these antennas melting because the plasma is hot. Some of the electronics that we had to be put together. And so this shows the time evolution of the plasma density. So this is time versus basically radius away from the center of this cylinder. This is showing the time evolution of the plasma. And if we look at the dispersion of waves at different times as this plasma develops, theoretically, we should see a change at, say, this frequency of 3 gigahertz, where first we're in this gap, except for the one topological wave, and then we start picking up some of the continuum. So we should see a change in the behavior. And we have seen such a change. This is a look at the power as a function of time and, again, distance from the center of the plasma. And it appears that we have a localized mode traveling along the edge of the plasma. And if we look at a time-lapse photo or video of this, it's a little bit hard to see, but there seems to be some sense of chiral motion here as the wave develops. So we have some tantalizing hints of this kind of chiral motion. So I'm almost done, probably near the end of my time here. So I want to close by telling you about some other surprising places where physics may have input to climate science. So one well, it's maybe not so surprising, but there's the GRACE satellites that have been measuring the Earth's gravitational potential very precisely and quantifying loss of ice in Greenland as it melts, changing the gravitational field. The Sacheverjev-Kitaev model, SYK model, that's well known to quantum condensed matter physicists, has been shown recently to be equivalent, at least at a classical level, to the direct interaction approximation that Einstein's last student, Bob Krejcinen, famous fluid dynamicist, introduced in 1959. So again, an example of two completely different fields that were working independently and kind of got to the same place, but were unaware of each other's work. One of my colleagues is using differential geometry as learned from general relativity to prove ocean turbulence models, where the stratification in the ocean forms curved surfaces. And so taking into account that curvature can lead to improved ways of modeling ocean turbulence. Cloud nucleation has been studied by particle physicists at CERN and trying to understand the role of cosmic rays in the climate system. And a number of us have been investigating the possible use of quantum computers for climate modeling. So asking the question, can quantum computers convey some advantage for climate modeling? I don't know the answer to that, but we've been using quantum computers to simulate classical nonlinear dynamical systems and very simple ones. So that's still at the very early stage. So Nature magazine, a few years ago, had this article, Physicists, Your Planet Needs You. And it was focusing on a central weakness of current climate models, which is in the description of clouds, and suggesting that physicists could contribute to better understanding of cloud physics. Now, there are a lot of climate scientists who identify as physicists. They got their undergraduate degrees in physics departments and maybe even a PhD in physics, or commonly moved into atmospheric science or physical oceanography. But what this is saying is that physicists that are sort of working in areas like condensed matter physics or particle physics have skills that could be applied to the climate problem, and that we very much need that kind of input that can help strengthen the overall effort when we join with geophysicists, biologists, and so on. And so since I'm vice president of the APS, I would be remiss if I didn't urge you to join our topical group on the physics of climate, which is focused on just trying to make these sorts of connections. So thank you very much.
One question at the beginning of your talk, you mentioned a gauge invariant description of these modes, but what's the gauge invariance?
Right. So when we're finding the normal modes of a wave system, then those wave functions are defined up to an overall phase. We can always, there's some arbitrariness in finding an eigenvector, right? We can multiply by a phase. So, but what we want to do is isolate the internal phase difference between the components. And so by making this product of the two components of the wave function, then that's focusing on what's the relative phase between, say, the y component of the velocity and the height. That's the thing that is the physical information. So sort of the starting point of the wave isn't so important. What we want to know is the internal phase difference. So calling it gauge invariance maybe makes it more mysterious than it really is. It's just looking at this internal phase difference.
Right, does the band gap shrink as you move away from the equator?
the band gap increases. So the band gap depends on the local pendulum frequency F. And so as we move away from the equator, it gets bigger and bigger. And it collapses at what we call a Weyl singularity at the equator. And that's where this topological phase transition occurs, where the bands are inverted. And but when we were looking at that phase singularity, we wanted to stay away from the equator so that we were clearly in the gapped region.
Yes.
So one of the forefronts of condensed matter is obviously topology together with strong interactions. And so this was topology in a linearized sense, so say non-interacting fields.
Yes.
So if I were, is there any sort of thing in climate that we could expect where non-linearities in the wave equations together with the topology can give us like crazy phenomena like fractional Hall kind of things?
I don't know about fractional, Paul, but absolutely, including the nonlinearities is, I think, a very interesting project and something we've been thinking about. I think mathematicians should think about, and I think there could be surprises. Maybe this Madden-Julian oscillation will force us to think about that, or almost certainly it will. There's also another thing I've been wondering is whether there's some combination between soliton physics and these topological waves. So if we have refinement in one dimension and we have dispersion, then we can turn on nonlinearities. Maybe something interesting will happen there. So that's wide open, I think. And we don't really have the tools yet to think about this. So I think there's room for lots of adventures.
Okay, so I guess that the room is very quiet because you overwhelmed people with topological information. Thank you very much.